Okay. So, last class we ended here, and this E of this vector E of V n I called V prime n, which is not random, but a vector which is function of n. So, this evolves like this from V prime n plus 1 comes. All right. Now, I replace R by this. So, I will have identity matrix minus mu T D T H V prime n. All right. Identity matrix I can write as T I T H. I into T H is T H, T T H is identity because it is unitary. Okay. I take this T common outside T and T H on the right hand side common, T H that goes to the right hand side, T T comes to the front. So, still I minus mu times D and then V prime n, this V prime n. So, nothing T I T H, that is what I have here, then minus mu T D T H, all right. And then now I multiply LHS and RHS, it is called pre-multiply, then multiply here, pre-multiply by TH. So, TH times this is TH times this, but THT is identity. That means, TH is I minus mu D, again TH V prime n. So, now this TH V prime n, I call it UN, just give a name. So, this is nothing but TH V prime n plus 1, so it is UN plus 1. Remember one thing, if I see the norm square of UN, that is UN vector, if I take every element, square up each element and then add, okay, there is a norm square, square of the length. So, that is like UN transpose with UN, but UN is T Hermitian V prime n, right. So, I have, if I put that here and transpose of that, in fact, instead of transpose I can also write it H, though they are all real. So, H and T will be same here, because there is nothing complex. So, Hermitian transpose is ordinary transposition, but since I am following H here, let me be consistent. So, let me put H n, UH and UN. So, if this is UN, UH n will be H on this. So, V prime H n, V prime H n, T H H which is T, and then again UN. So, UN directly T H and T T H is identity, this is identity. So, it is nothing but V prime H V prime, which is nothing but V prime n norm square. So, you see UN and V prime n, they have the same length, same power, that is same norm square. If one is obtained from the other by pre-multiplying by a unitary matrix. That is why I say unitary matrices preserve norms. Norm of the original vector, that is length of the original vector, and after the transformation by TH, this vector, they are the same. Norm square of UN and norm square of V prime n, they are same. Therefore, if I can show that with time, this norm square of UN, this goes down to 0, that will also mean norm square of V prime n will go down to 0. Okay, that is how I will proceed. And norm square of V prime n is this much. So, and norm square going to 0 means, norm square of a vector 0 means vector itself is 0. That I told several times earlier. Any vector, its norm square, if it is 0, that means only possibility vector itself is 0. So, if this vector norm square goes to 0, that means as n tends to infinity, if I can show that, that will mean this vector itself goes to 0 as n tends to infinity, which will give rise to convergence. That is, this error convergence in mean, there is error vector after expectation, that is after mean, will become 0 as n tends to infinity. So, and error vector 0 means W opt and W n, they will be together, they will be same, then only the error between them is 0, which is V n. This is what I will show. Okay. So, I will show norm square of U n goes down to 0 as n tends to infinity, which means norm square of V prime n goes down to 0 as n tends to infinity. Norm square of a vector going down to 0 means vector itself goes down to 0 as n tends to infinity, and this is V prime n. So, E of this goes down to 0 as n tends to infinity, and E of this is going down to 0 means V n is W n minus W opt. That difference, that is E of W n minus E of W opt, W opt is constant. So, E of W n minus W opt, that goes to 0 means E of W n goes to W opt. I will show that. This is my game, all right. And one more thing you see, I minus mu d, I is a diagonal matrix with 1s in the diagonal places, mu into d, d is a diagonal matrix with the eigenvalues. Okay. So, together is a diagonal matrix. So, it will be like 1 minus mu lambda 0, 1 minus mu lambda 1 dot dot dot, 1 minus mu lambda k dot dot dot, 1 minus mu lambda n minus 1. All lambdas are real. This side all 0, this side all 0. These are the matrices. This matrix multiplies u n. So, top guy of u n, call it u 0 n. That will be multiplied by this only. It is a diagonal matrix. Next guy u 1 n, that will be multiplied by this guy only, likewise. Okay. That means it will be like one minus mu lambda 0 u 0, top guy u 0 n, then 1 minus mu lambda 1 u 1 n dot 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 lambda k u k n and dot 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 1 minus mu lambda n minus 1 u. So, u n plus 1 is just this. So, norm square of u n plus 1 will be norm square of this, but norm square of this is square of this term plus square of this term plus dot 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 square of this term plus dot 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 square of this term. This is what I will write in the next page. So, norm square of will be 1 minus mu lambda 0 square 1 minus mu lambda square u 0 square n, and likewise plus dot 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 in general 1 minus mu lambda k square u k square n plus dot 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 1 minus mu lambda now. Okay. This also means, but I will use this expression little later. Let me again sorry. So, this is my I minus mu d into u n. This u n itself I can write as u n, like instead of n plus 1 if I write n. So, it will be again same matrix I minus mu d into u n minus 1. Again u n minus 1 is I minus mu d u n minus 2, and like that. So, that way what I had is u n you write as because this is independent of n. So, u n again, if I replace n plus 1 by n, it will be I minus mu d u n minus 1. So, I minus mu d u n minus 1. So, square u n minus 1 and dot 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 dot. If you go on doing it, finally I minus mu d square cube like that. I write here what it is, but it will be u 0. U 0 I will stop. So, if it is n minus 1, it is 2. Okay. It is, if it is 0 means n minus n, so it will be n plus 1. N plus 1. This is what. And u 0 is a constant. U 0, because what is u 0? U 0 is what is u n after all? This is u n. So, u 0 is t h v prime n. Okay. And what is v prime n? E of v 0, sorry, t h v prime 0. U 0 is t h v prime 0. And what is v prime 0? E of v 0. But v 0 is w 0 minus w opt. This is an initial condition which is not random. This is not random. So, v 0 is not random, E of that is itself. That is why there is a constant. So, u 0 is a constant. This time this. This means diagonal matrix into diagonal matrix into diagonal matrix, that will be a diagonal matrix, right. So, it will be 1 minus mu lambda 0 n plus 1 times. Look, we are going on multiplying I minus mu d, I minus mu d, I minus mu d, I minus all diagonal, it will be this. Then 1 minus mu lambda k whole to the power n plus 1, 1 minus mu lambda u 0. So, now like this we can write as earlier I had the square, now it is, this is the only difference, n plus 1 times the 0th component of u 0 square. Dot 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 lambda k to the power n plus 1 again, kth component square, and dot 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 1 minus mu lambda n minus 1 to the power n plus 1, the last component. That's compared to u 0, that is this. Now, if we have 1 minus mu lambda k, its value, if its magnitude lies between 0 to 1, then as we power it up, n to n plus 1 to n plus 2 to n plus 3 n plus 4, this goes down, because it is less than 1 in magnitude. Suppose it is half, but 1/3. So, 1/3 to the power n plus 1, then 1/3 to the power n plus 2, then 1/3 to the power n plus 4, as we go on iteration. Value is decreasing, decreasing, and finally it will go down to 0. And if all goes down to 0, this also will go down to 0. So, a strong condition, sufficient condition for these to go down to 0 will be if everybody has a magnitude between 0 to 1. That means its value is between 1 to minus 1. Okay, it can be minus 0.3 also or plus 0.3 also, does not matter. Magnitude should be less than 1. Then only as we go on doing it, its magnitude finally will go down to 0. Okay, so this should be true for all lambda k. This means if I take this part, then you take this to this side, minus 1 to this side. So, that means mu less than 2 by lambda k. And if I take this inequality, 1 cancels. So, minus mu lambda k less than 0, mu lambda k greater than 0. lambda k is totally real, it is positive because this is a eigenvalue of the input autocorrelation matrix which is assumed to be positive definite. So, if that is positive, mu must be positive. So, that is what, then only this is greater than 0. So, this is the range. Now, 2 by lambda 0, 2 by lambda 1. So, minimum is 2 by lambda max. Lambda max means the eigenvalue is the highest magnitude. All are positive. So, highest positive value. Then 2 by lambda max is the minimum. So, mu should satisfy that also. Then it will be satisfied, mu will be satisfied, mu less than 2 by lambda k will be satisfied for other eigenvalues also, if this is satisfied, because this is lambda max. So, 2 by lambda max is the minimum value of this. Okay. For any other lambda k, 2 by lambda k will be larger than this. So, if mu is less than 2 by lambda max, mu is automatically less than 2 by lambda k. So, this is the condition we have for convergence. Okay. This is a condition of convergence, but convergence means convergence in mean. Okay, convergence is mean, that is what I find from here, limit n tending to infinity u n vector, its norm or norm square goes down to 0, which means since norm 0 means vector itself is 0, it means limit n tending to infinity u n vector itself goes to 0. The 0 vector, this is a scalar norm, this vector. But what was u n? U n from the previous page we can see what was u n. U n is T h v prime n. Okay. Oh, 1 minute. U n is T h. So, both have same norm. U n and v prime n, they have the same norm. And that is what. So, I should use that. It is v prime. You see here, u n and v prime n, they have the same norm. So, if this norm goes to 0, this norm goes to 0. This implies limit goes to 0, and then I say if the norm is 0, vector itself goes to 0. Okay. That is the only way a norm can be 0. So, this means limit n tending to infinity v prime n goes to 0. But v prime n is, in the previous page you have seen, this is v prime n, E of v n, and v n is w n minus w opt. So, limit E of v n, and v n is w n minus w opt, this is your v n, this goes to 0, which means E of w n minus E of w opt. W opt is constant, so E of w opt in itself. That means, next page I go, E of w n limit n tending to infinity is w opt. That means, expected value of each weight converges on the corresponding optimal value. That is what I had shown, mean of the fluctuation converges on the corresponding optimal value, but not the coefficient itself. Okay. One more thing, we know trace is a sum of diagonal elements we have seen. We also know, if I give you R, which is a positive definite matrix, trace of R is a summation of all the eigenvalues, right. So, trace of R, this should be greater than or equal to lambda max, because trace of R means lambda max plus summation of other eigenvalues. Okay, so, it is greater than or equal to lambda max. In fact, if it is strictly positive definite, other eigenvalues also are positive, lambda max plus other, nobody can be 0. So, it is actually strictly greater than, all right. So, under that assumption, let me make it strictly greater than. Which means 2 by lambda max is greater than 2 by trace r. So, if our condition was this 2 by lambda max, but finding eigenvalue and all that is cumbersome in practice. Trace of r is very easy, the summation of the diagonal elements, no computation of eigenvalue and all that. So, if mu is less than 2 by trace r, mu is automatically less than 2 by lambda max. So, that is why we modify it to this mu less than 2 by trace r. If this happens, it will always converge in mean. Convergence in mean is guaranteed. Okay. This was also fine, but this requires is a bit impractical because it requires computation of eigenvalues and all that. That's for big matrices is very difficult, cumbersome actually. So, this you can do very quickly. So, this is what is usually followed, mu greater than 0 less than 2 by trace r, all right. So, this is how I have given the proof of LMS algorithm, and LMS algorithm I mean schematically is shown like this: x n w 0 n dot 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 w k n this is y n So, there is an adaptation part, LMS, that takes the input data, because the adaptive part, the update part was mu x n vector E n. So, x n vector has x of small n plus past terms. Past terms are already in the system. So, current term has to be taken. So, adaptation takes that vector, then has that vector, and it needs E n. This is my E n, this also goes in, and it calculates that update formula, update equation, by that it calculates W n plus 1. So, once it is updated, it changes them for use in the next clock cycle, and this is how it is indicated: tuning, training. So, this is a schematic of LMS based adaptive filter, all right. Now, instead of going further on the theory and other forms and all that, I will take up examples, several examples, so application examples, all right, of adaptive filters. These application examples can be classified into two types. First is forward modeling. Suppose I have got an unknown system. Modeled as LTI, linear time invariant system, linear shift invariant system. Such modeling often requires the filter order, usually a FIR filter, to be large. By a large order FIR filter, you can model an unknown system. Okay. So, the coefficients are h 0, h 1 dot dot dot, maybe h n minus 1. Then I have to identify them, estimate them, and they may be varying with time, from time to time. So, I should be able to track them. That is a model, forward modeling. Okay. So, when you observe, I mean you give a WSS input to the plant, that you can generate in the lab, it is not a problem, WSS input to this. Okay. Output, when you observe, as this input goes through the system, at various points some noise gets added. So, all the noise effects you can combine together, add as a separate noise component Zn, and this is Yn. I should not use the term Yn, let me use it, let me use something maybe Vn, and this is what you observe. So, plant output when you observe, you do not get the pure raw Vn, you get a noisy version Dn. Okay. Now, suppose my question is you want an optimal filter W opt, it has W0, W1 dot 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 W n minus 1. It is assumed Xn is 0 mean and therefore Vn is 0 mean, Zn is statistically independent with input, very natural, is a noise generated inside the system, it has nothing to do with the input. So, you can assume that to be independent of each other, all right. So, if you want it to be, if you want this to be an optimal filter, so that output error minimum, variance is minimized, the W opt will be what? We know the formula R inverse P, right, R inverse P. P is the autocorrelation between Xn vector and Dn, and R is the input autocorrelation. Now, what is Dn? Dn is Vn plus Zn. And what is Vn? Vn is Xn transpose H, and this plus Zn. What is H? H is the true system coefficient vector. I do not know them, I have to find them. True system coefficient vectors. So, linear convolution. So, either Xn transpose Hn, Xn transpose H or H transpose Xn, they are same. So, I write it as Xn transpose H, that is Vn plus Zn, that is my Dn, and Zn is statistically also 0 mean and statistically independent with Xn. So, P will be what? E of Xn Dn, and now replace Dn by this. So, Xn X transpose n H plus Xn, Zn is a scalar. So, I should not put this. So, Xn into this part I have done, Xn into this part and Xn into Zn, all right. Now, all the elements of Xn and elements of Zn, they are statistically independent. So, expected value of a product will be expected value of this into expected value of this, each is 0 mean. So, if you take expected value of this vector times Zn, every element will be after expectation will be 0, because they are statistically independent. So, E of E on a product of any term of Xn into Zn will be E of that Xn term into E of Zn term, and each is 0 because they are 0 mean. So, that goes to 0, and E on this part and H is not random. So, it will be E on this into H, this is R. So, this will be your RH, R is the autocorrelation matrix, which means in this case the optimal filter will be R inverse RH and it cancels H, which means if I know the value of capital N correctly and calculate the optimal filter in this case using this as Dn, plant output, noisy plant output as Dn and input Xn, that optimal filter will be the actual true system parameters. This is called forward modeling, okay, because I am going, I am trying, input is going in the forward direction and that is what I am modeling. Okay. This is the basic scheme, and this scheme has been used in several contexts which we will consider, okay, forward modeling as some applications. So, that will be in the next class. Thank you very much.